Hello, my name is Scott Landau, and this is the Physics 2212 lab number 3. So, to the introduction. The purpose of this lab is to investigate the magnetic field of the bar magnet and find the experimental value of the magnetic dipole moment using this, and then compare the two models, including the one from glow scripts, of the situation to determine which one better represents the scenario. And some physics principles used are magnetism, magnetic dipoles, and the simplified expressions for the dipoles at different orientations. And you can see the formula below for the magnetic dipole. And in this experiment, we define the system to be the bar magnet and the magnetometer, and then the surroundings to be the rest of the universe. And initially, there's a fixed bar magnet at the end of a ruler, and a magnetometer, which is on our phone, is placed at a certain distance from this magnet. For the actual experiment, the magnetic field measurements were found at different distances away from the bar magnet. And then using the expression for magnetic fields of a magnetic dipole, we analyze the data in the formula shown below. And here's the data that we found. You can see the logarithmic graph um, of the magnetic field and the distance. And some observations that we made were that the magnetometer, when it's far from the magnet, it still measures a non-zero magnetic field in X direction. So there's always a magnetic field. And as the magnetometer goes closer to the magnet, the X component increases, it doesn't decrease. And then the position of the magnetometer does have an effect on the X component of the magnetic field, so you have to make sure that it's positioned correctly. And then the magnetometer, when it moves closer to it, it increases as well. And then after calculating the exponent of the R and the dipole behavior by using the slope of the logarithmic graph, the proportionality constant is found by calculating the dipole moment of the bar magnet, which is about 2.15 amp times meters squared. And there is lots of potential error in this experiment. For my group personally, it was very difficult to get the accurate measurements. And also the location of the magnetometer on the phone could be slightly inaccurate because a lot of the data, like moving it just a tiny little bit, changed the reading by a lot. And there's also external magnetic fields. So, for instance, some other group members could have had their phone on the table, which has a magnetometer and a magnetic field, or their computers on the table. So that could skew the data. Computational model. Um, Computational model used closed scripts and displayed this formula for the magnetic dipole. And arrows were also added to visualize this field at different locations. And then the model used to compare the computer magnetic fields with experimental measurements shown below. And here's the results. You can see the arrow of the magnetic field. And then what if we hadn't laid out the experiment accounting for both the magnetic north and south and instead used just a random intermediate egg because we had to position the ruler and the magnetometer and the bar magnet specifically so it was in the north direction, in the north-south plane. If this happened, then the x components would be offset by a constant because you'd be multiplying it by some sort of theta value. Um, and that impacts the magnetic dipole's experimental value that we found. And what if we stuck two identical magnets together at the end and then redid the experiment? If we did this, then there would be a stronger magnetic dipole um, that would be yielded, and all the experimental measurements, including the magnetic dipole moment, would be scaled up by the same constant amount. Thank you for listening to my experiments.